Myself Manish Parekh. I will teach you physics, and today's topic is the time period for simple harmonic motion. Let me write the topic. Time period for simple harmonic motion. Let us recall the theories, whatever you have done in your theory classes. This is rigid support and this is a weightless spring. It is obeying Hooke's law and the spring constant is K. Just now the spring is in relaxed position. I mean it is not stretched or it is not compressed one. Now I will suspend one mass m from it. Due to the weight force of this mass m, due to this weight force, there will be an increase in the length of the spring. The length of the spring is increased by this much. Let the increase in the length of spring is y. As according to the Hooke's law, some restoring force will be produced in the spring, and the restoring force is K times displacement of the object or increase in the length of the spring. This restoring force is in upward direction and this weight force is in downward direction. Just now this mass m is in equilibrium. That means it is not performing any oscillation. That's why the net force on this mass is 0. I can say that the force acting in the downward direction is same as the force acting in the upward direction. So mg is equal to ky. We can write that m by k is equal to y by g. If I pull this mass m in the downward direction and just release it, this mass will perform the simple harmonic motion with respect to this point. And as you have studied in the theory classes, the time period for that simple harmonic motion is this, or this m by k is same as y by g. Today in this short session I am going to consider some system of spring and we will find the time period for the object which is suspended from that spring. Let us see first case, a very normal case it is. This is a string. It is unextensible string. It's massless string. This is a pulley. It is also frictionless, weightless spring and pulley. Once string is passed over, at the other end, spring is attached. Second end of the spring is the fixed one. This is a continuous string. At the other end, mass m is suspended, but just now I am holding this mass. That means it is at rest. Even its weight force is not acting on it, and the spring constant of the spring is K. As I am holding it, there is no tension in the string, so spring is relaxed. There is no extension or compression in the spring. Now I am removing my stand from here. Due to this weight force mg, there will be a tension force in the string. The same string is over here. Due to this tension force T, the spring will be stretched. Let the increase in the length of spring is y. if the length of spring is increased by y, this mass m will come down by the distance y. As the length of the spring is increased by y, the restoring force produced in the spring will be in this direction and it will be ky. Now, if I allow this mass to perform the simple harmonic motion, in that case we want to find the time period, but this is the same case as this one because the displacement of the object is y and the increase in the length of spring is also y. So this case is not an extraordinary one. So the time period will be of this type. Now let me make some changes in this figure. Even this end is fixed and I have attached one spring over here. Its spring constant is k. One mass m is over here. This mass m. This mass is at rest. That means I am holding it. I have not allowed it to come down. That means if I am holding it, there is no tension in this string, even there is no tension in the spring. It is also a relaxed spring. There is no extension or the compression in the spring. Now, as I will remove my hand, this weight force will start functioning. Due to this weight force, there will be some tension in the string. The same string is over here, so even in this string, the same tension T is there. Now, due to this weight force and this tension force, these two forces are pulling the point O in the downward direction. So this mass will come down by some distance. Like the mass has been displaced by the distance y. If mass is coming down by the distance y, the increase in the length of the spring will be y by 2. This can be understood in this way, as this and these two forces are pulling the system in a downward direction by the distance y. This part, both of the length y by 2 are being available to this. That's why it is coming down by the distance y. So this point O is coming down by this length only. So the increase in the length of spring is y by 2. As the length of the spring is increasing, some restoring force will be there in the spring in upward direction. And as you know, the restoring force is k times increase in the length of spring. Here, the displacement of the object is not same as the increase in the length of the spring. That's why you cannot make use of this simple formula. We have to derive some equivalent force constant for this system, and we have to substitute that equivalent force constant in this formula. Then only this can be a useful form. So let me consider some equivalency about this. This mass is at rest, so for equilibrium of mass m, for the equilibrium mass m, this mg and t are balancing each other, so I can write t is equal to mg. Now this t and this mg, these two forces are pulling the system in downward direction, and this restoring force is pulling the system in upward direction. still the system is in balance, in equilibrium. That's why we can think about the equilibrium of point O for the equilibrium of point O, the forces acting in the downward direction is T plus mg, and the only force acting in the upward direction is this restoring force, that is K y by 2. But from equation 1 we have T is equal to mg plus this mg is there. So we have 2 mg is equal to ky by 2. I will need this mg afterwards. So mg is equal to ky by 4. Now, as the displacement is not same as the extension in the spring, I have to consider one equivalent spring. Imagine that this is an equivalent spring. Its spring constant is K equivalent. What we mean by equivalency? The equivalent spring means a spring which can perform all the characteristics of the system. Then what is the characteristic of the system? If we suspend mass m on it, it will be displaced by distance y. So over here, if I will suspend one mass m over here, due to its weight force, it will come down by distance y. The increase in the length of spring will be also y in this case. So the restoring force produced in the spring is this much. Even this mass is at rest, it is in equilibrium, so I can write this K equilibrium y is equal to mg, and this mg is equal to ky by 4. This y by cancel, so we got an equivalent force constant. Now for this case, we can apply the formula for the time period. The mass suspended is m, K equivalent, and the equivalent force constant is K by 4. So your answer is, so it is 4 pi m by k. That's all. See, we have solved this problem with the help of some equilibrium of this mass m, equilibrium of point O. But this problem can be solved with the help of some conservation law. We can apply the law of conservation of energy over here. Let us try in that method, because in many cases it will be comfortable to you to solve the problem with the help of those principles. How can we apply the law of conservation of energy over here? First of all, imagine that this mass m is already suspended, the spring is under tension, there would have been some initial increase in the length of the spring, that is y0, but we will ignore this extension and we will start from the reference point y is equal to 0. That means now I am stretching this mass m in the downward direction by distance y and just leaving it, and m is performing simple harmonic motion. At some instant of time, let me take at time t is equal to t, this mass m is over here, so the displacement of mass is y. It is not stationary one, it is oscillating, so it must have some velocity at that instant and at that point. Obviously mass m is coming over here, there must be some increase in the length of the spring. So as per our previous discussion, if mass m is coming down by the distance y, what will be the increase in the length of this spring? These 2 points has come down by y by 2. So the increase in the length of spring is only y by 2. So in this case, let us apply some law of conservation of energy. I will make use of this principle in a way that whatever the amount of energy lost by the object or the system, and I will compare that with the energy gained by the system. Loss of energy is equal to gain in energy. What is the loss? Initially the mass was over here. At the end, at this instant, the mass has come over here. It came down by the distance y, so it is losing its potential energy, gravitational potential energy, by mgy. But as the mass has come over here, it has acquired some velocity, so it must have the kinetic energy. But due to this moment of mass m, there is an extension in the length of the spring, so spring is getting some elastic potential energy, that is half k y square. Before differentiating, I will simplify this equation. Mgy 2 square is 4 to the 8, 1 by 8 ky square. Now I am differentiating this equation with respect to time to get the acceleration. The differentiation of the displacement will give you velocity. The differentiation of v square is 2v, and the differentiation of v is acceleration. The differentiation of y square is 2y, and again the differentiation of y is velocity. In all these problems, velocity will be cancelled. We can divide the equation by y or v. So I get mg is equal to ma plus 1 by 4 ky. Now let me divide the equation by small m. So I will get g is equal to a plus k by 4my. So I can write it like this: acceleration is equal to g minus k by 4my square. As you know that in the simple harmonic motion, the acceleration is directly proportional to the displacement, and it is in the opposite direction of the displacement, and we get the proportionality constant omega square. So comparing these two, we get omega square is equal to k by 4m. So omega is equal to under root k by 4m. Omega is 2 pi by t. So So you will get E is equal to twice pi under root 4my. This is the same answer what we have got from the previous method. But in previous method, I considered the equilibrium of the system, and over here I considered that this is performing the simple harmonic motion and it is at some distance y from the origin. Now if we have time, we can mix up these two problems. Whatever I have discussed, I will mix up these two problems and we will solve it again. Let me give it name the spring 1, and as I told you, I will mix up these two problems, and the spring constant of this spring is K2. At the end of this string, one mass M is suspended over here, but just now it is at rest. I am holding it, so there is no tension in these two springs. There is no tension in this string. Now I am just leaving this mass M. So due to its weight force mg, this string will come under tension. There will be tension in this string. The same tension will be over here. This tension will pull this string. So there will be some increase in the length of the spring. Imagine that the increase in the length of this spring is y2. So obviously this object will come down by the distance y2. Now, as the length of this spring has increased by y2, some restoring force will produce in this in the downward direction, and that is K2y2. Now, what happens about this spring 1? These two forces are pulling the system in downward direction. That's why this point O will come down. That's why the length of this spring will also increase by some distance. Let me take that. Increase in the length of this spring is y1. So this point O will come down by distance y1. So this y1 length and this y1 length will get available to this. So this object will come down by the distance 2y1. So the total displacement of this mass is this. Now, just now this M is under equilibrium. It is not oscillating at all. If we allow it to oscillate, what will be its time period? That we want to find. In that case, I will use the phenomenon of the equilibrium only. For the equilibrium of M, this T is equal to mg. Again, this T, the same tension, has extended the length of this spring. So this T is nothing but this restoring force. This T is K2y2. So by equating these two, I will get K2y2 is equal to mg. So y2 is equal to mg upon K2. Now let us consider this point O. Point O is also under equilibrium. So for the equilibrium of point O, the only force acting in the upward direction is K1y1, and this and these two forces are acting in the downward direction. So sum of these two must be balancing this. So let me write the sum of these two. K2I2 plus mg. But you know that K2I2 is equal to mg. So K1Y1 plus mg that is 2mg. So I will get Y1 is equal to 2mg by K1. Now we want to obtain the time period for this mass m, but the displacement of the object is very awkward. It is not equal to the increase in length of the spring. So I have to consider one equivalent spring. Imagine that this is an equivalent spring. Force constant is kq. The same mass m is suspended from it, and due to the same weight force, the displacement of the mass becomes y, extension in the spring becomes y, and this y is equal to this. Then only it is the equivalent spring. So the restoring force in the spring is K y. This m is under equilibrium. So these two forces must be balancing each other. So K equivalent y is equal to mg, but this y is here, y2 plus 2y1 is equal to mg. We have these ready-made values of y1 and y2. I will plug in these values over here. This y2 is mg upon k2. This y1 2mg by k1. This mg is over there. We can divide the equation by mg. So I will get K equivalent 1 over K2 plus 4 by K1 is equal to 1. So 1 upon K equivalent is 1 by K2, 4 by K1. Now the time period for this equivalent spring is, this K equivalent should be used over there. I can write it like this. So 1 upon K equivalent is this 1 over K2 plus 4 upon K1. So this is the required time period of this mass if it is allowed to perform the simple harmonic motion. Even if we have enough time, we can solve the same problem by the same method which I adopted in the previous sum, the law of conservation of energy. We will discuss it later on. If you have any confusions, you can ask me. Thank you. Okay, no?